Hello, everybody. Welcome back. This is Math 1375, Professor Reitz, and today we're going to be talking about chapters 15 and 16 in the book, Applications of Exponential and Log Functions. Just as an aside, I hope everyone is doing well in staying at home and avoiding other people to the extent that you can. You should know that I'm at home in our one-bedroom apartment in Queens with my wife and two children, and they're currently out in the other room watching the incredible movie The Three Amigos. And so if you get a little bit of background noise, that's what that is. Okay. On with exponential and log functions. The point of today's lesson is, and really the point that we've of studying exponential functions, is that they are amazingly and even staggeringly useful in describing certain things that happen in the real world. And we're going to see some examples of that today. And the things I want you to watch out for today are understanding the examples, following the steps that you need to do to figure out which numbers go where and so on, but also trying to get a sense of what exponential functions mean. And there's a general idea in exponential functions which we haven't gone into too much detail of here. You will see much more of it in calculus, but that idea is that an exponential function is a function where how quickly it grows is proportional to how big it is. So when an exponential function is small, it grows pretty slowly. But when an exponential function is large, it grows very quickly. And that means once an exponential function gets large, it gets even larger, even faster. Okay. You might recall that an exponential function is a function f of x equals c times b to the x, where c and b are real numbers. And then we also have this restriction: b has to be positive. We have to have the base be positive, and we're going to just assume that the base is not equal to 1 for these, and that's because if the base is equal to 1, then no matter what x you plug in there, it's just 1 to the x. It doesn't change the function at all. It becomes a constant function if the base is 1. We've already studied constant functions. Okay. So if I tell you something is an exponential function or is modeled by an exponential function, you know that its formula is going to look like this. This is like the standard form of an exponential function. And so in order to actually determine what this function is, you just need to figure out what is this number b, what is the base, and then what is the coefficient, the number in the front, the c. So that's what we're going to be working on here. And it turns out, since there are two unknowns, if I give you an exponential function and I tell you 2 points on that function, if I tell you what is the x and the y, or the x and the f of x, for 2 points, we should be able to use those 2 points to find b and c. That's what we're going to start with next. This is not a real-world example. This is just a working with the formulas, but we're going to be using this idea when we go on to talk about real-world examples. Okay. Let's take a look. This is from example 15.1 in the book, and I'm only going to do parts A and C. So let's start with part A. In this one, we're told that f of x, in example 15.1, we're told that this is an exponential function. So what do we know? We know that f of x must equal something c times something b to the power x. And we just have to find c and b. And we're told the following two pieces of information: f of 0 equals 4, and f of 1 equals 20. So here's what we're going to do. It's extremely helpful that we're given this fact that f of 0 equals 4, in particular that this input is 0, because what we're going to do is we're just going to plug in the point 0, 4 into our function, into our formula, plug in when we plug in, the formula that we're going to be using is this one. We know this is what our function looks like. We just don't know these numbers. And this tells us a pair of values. The 0 is like the x. It's going to go up here where the x goes. And the 4 is what the entire f of 0 is equal to. So whatever we calculate, c times b to the x to the 0, the whole thing should equal 4. So we're going to put the 4 in the place of the f of x. Here's how it goes. We substitute in 4 is equal to c times b to the power 0. Now, this doesn't seem to help, but what's nice is that b to the power 0, since we've decided ahead of time, since f of x is exponential, it means that b is positive and is not equal to 1. That means any positive number, if you raise it to the power 0, is just equal to 1. So this entire thing is just equal to 1. So here we have that 4 is equal to c times 1. And of course, c times 1 is just c. So this tells us that 4 is equal to c, or c is equal to 4. So we found one of our two numbers already. Looking at our formula up here, we've already found the number out in front. Yeah. You'll also observe that the value of the function when x is 0, so when you plug 0 in, you get a 4, that's always the number that turns out to be this number in the front. So when you're looking for c, if you can find the value of the function when x is 0, then that number that you get there is going to be right in there. And that is going to happen in general. Okay, so now we're going to use the second bit of information here. We're going to use the fact that f of 1 is equal to 20. That means the 20, that's equal to f of 1. 1 goes in for the x, and 20 goes in for the f of x. That is to say, 1 is the input, and 20 is the output. So it looks like this. 20 is equal to c times b to the 1. And of course, we also know c, so we have 20 is equal to 4 times b. Now, b to the 1 is just b, so 20 is equal to 4b. That's substituting in. And we can get the b by itself by dividing both sides by 4. Here on the left-hand side, we get 5, and on the right-hand side, we get b, so b is equal to 5. Putting these together, our goal is to find a formula for the function f of x, and in this case, f of x is equal to 4 times 5 to the x. That's it. Okay, I encourage you to pause, take a look at the next part, which is part C, and then come back and work through it with me. All right, here we go for part C. In this case, we still know that f of x is exponential. This is a different f. It's a different function f of x, rather. It's a new problem. F of x is exponential, so that we know f of x is equal to c times b to the x. And once again, we have to find c and b. Let's go ahead and just do the same idea. Here, we know that f of 2 is 160, and we know that f of 7 is 5. Okay, so let's start with that f of 2 equal 160, and let's plug in. The 2 is the x, which means the 160 is the f of x, so 160 is equal to c times b to the 2. C times b squared equals 160. Now this is annoying because here we don't have the input being 0, which means that b to the 0, we don't get that disappearing. This is b squared. Whatever b is, that number squared appears here. And so unfortunately, we don't eliminate one of the variables immediately. This is in contrast to the situation in the first part A, where the b immediately disappeared and we were able to get one of the variables. So what do? We just pause right here, and we go ahead and plug the other one in also. And in this case, the input, the x, is 7, and the output, the f of x, is 5. So 5 is equal to c times b to the 7. Okay. Well, we have two equations, and they have two variables in them. They have c and b in them. And what we need to do is somehow rearrange them in such a way that we can eliminate a variable. And what I'm going to do is use the fact that if you have two equations, you're allowed to divide both sides. In particular, I can divide this equation on the left by 5 and on the right by cb to the 7. I divide one equation by another. So what do we get? We get 160 over 5 is equal to cb squared over cb to the 7. Let's give ourselves a little bit more room here. 160 divided by 5, that is arithmetic. Go ahead and do it on a calculator. I believe the answer is 32. So on the left we have 32. And on the right, we have some things that we can cancel. So let's go ahead on the right. We're going to cancel a c out of the top and bottom. That's nice because there are no more c's in this equation anymore. And then we can cancel some of the b's. There are 2 b's on top, b squared, and 7 b's multiplied on the bottom, b to the 7. So if we cancel 2 of the b's, we cancel out both of those, and this 7 now becomes a 5. We've used up 2 of them. So I think altogether, when we collect all of the pieces, what we have left on this side is a fraction. It's 1 over, and it's b to the power 5. And all we want to do is get b by itself. Instead, I'm going to take this equation. I'm going to think of it as being 32 over 1. And I'm going to cross-multiply. Another way to say it is just to say that I'm going to multiply both sides by the same thing, which is by b to the 5th. So if we say this is times b to the 5th and times b to the 5th, then on the left we get 32b to the 5th, and on the right everything cancels and we just get 1. Okay, working to get the b by itself. Now, I'm going to divide both sides by 32. So we have that b to the 5th power is equal to 1 over 32. And then the last thing to do is to get rid of that 5th power, and we can do that by taking the 5th root. So if we take that b to the 5th and we put a 5th root over it, then we get to do the same thing on this side, 5th root of 1 over 32. On the left-hand side, the 5th root of b to the 5th, they cancel out. That rule that they cancel out works just fine if the power is a odd number. And if it's an even number, then it works provided the number inside, that b, is a positive number. And we know b is positive. So canceling on the left, we get just b. And on the right, we have the 5th root of 1 over 32. Now, there's different ways to figure this out. You can plug it into a calculator. You can do 1 divided by 32, and then you can do 5th root. You can also change that 5th root into a power of 1/5, if you wish. That would be an alternative approach. However you do it, another way to do it is to distribute the radical to the top and to the bottom. However we do it, we should end up with the following: 1/2. I'll put in a middle step like this. The 5th root, if we distribute it to the top and bottom, is the 5th root of 1 over the 5th root of 32. The 5th root of 1 is just 1, and the 5th root of 32, well, I happen to know 32 is a power of 2, and if we're lucky, then it's the 5th power. So 32 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That was 5 2's that I multiplied together. So that means 2 to the 5th is 32, which means the 5th root of 32 is 2. In either case, if that sounded like nonsense coming out of my mouth, I apologize. In either case, we get an answer for b, which is b is 1/2. Okay, so we now know that our function that we're looking in, f of x equals c times b to the x, what it looks like is f of x equals c times b to the times 1/2 to the x. And now what we do is we take either one of these equations and we replace the b equal 1/2 in that equation. That's what's going to allow us to find c. Let's do it in this one. So from the equation 160 equals cb squared, we're going to replace or plug in b equal a half. We've learned what b is equal to. It's equal to 1/2. There we go. So this is 160 is equal to c times 1/2 squared. Now, this only has one variable in it. It only has a c in it for a variable. And to solve the rest, well, first I square the 1/2. When I square the half, I get a fourth. So c times 1/4, and that's equal to 160. Now, to cancel off the fourth, what I'm going to do is I'm going to multiply both sides by 4 times 4 and times 4. On the right-hand side, everything cancels except for the c. And on the left-hand side, we have 4 times 160. That, once again, is a calculator problem, or you can do mental arithmetic if you want. Let me see. 4 times 160 is the same as 2 times 320, which is the same as 640. So, unless I've mentally calculated wrong, I have that c is equal to 640. And what is our final answer for this thing? Well, they want to know what is a formula for this function. This is in part C, and the answer is f of x is equal to 640 times 1/2 to the power x. That's my final answer for part C. I want to make two comments about these two B and C that we found here. The first is when you go back and you look at the original function values, let's just look at them one at a time. In the beginning, the way we think of it is if we start with x as 0, we get a 4. If x increases and goes up to 1, we get a 20. And so what's happening is as x gets bigger, the output is increasing. If the output is increasing, then in an exponential function, what that means is that the base must be bigger than 1, because that means every time you increase x, you're multiplying essentially by another number bigger than 1, by another b. It should not be a surprise then in part A that our b was equal to 5. That's a number bigger than 1. Now in part C it's a little different. Here we start where x is 2 and the output is 160. When we get up to f as 7, the output has fallen all the way to 5, which means that as x is growing, the y is getting smaller, and that corresponds to the base being less than 1. And you'll notice that here the base was 1/2. In fact, all the way down here it is 1/2 to the x. You can see as x gets bigger, we're going to be increasing the power on this half, and that's going to be making the entire output value smaller. Okay, that's it. Next, we're going to look at some applications in the next video.